All right, so what we have now is a plate with a ideal crack in it. So I'm drawing it in only 2D. We know that the thickness is largely irrelevant. There's a certain height. Presently, I'm assuming that that height is sufficiently large with respect to the half width of the plate. And then there is a hole which is so thin that it represents a slit, or what we call now a crack. And that crack has half width A or total width 2A. We have to remember always that A represents the half width of the crack, and I have so far also assumed importantly that A is much less than B. Okay? Now under those assumptions, we know that the stress concentration at the tip of the crack is so large that actually the normal stress in the y direction is infinite. Okay. Now, what we would like to do is we would like to somehow have a explicit mathematical representation of the stress field, including the normal stresses in the y as well as in the x direction. So that's y and that's the x direction, as well as the shear stresses. Not as I move only along the x direction, but along any direction at the tip of the crack. So what I will do now is I will concentrate in a region that is in the vicinity of the crack. Okay? And I will zoom into that region. Okay? And I will depict the crack surface as such. Now I'm putting a visible distance between the surfaces of the crack just for visual purposes. What we have assumed is that the height of the crack is 0. So there is no width. We just have two surfaces that are not attached to each other. They are free to apart from each other, but if I press, they will press against each other, but they are free to part from each other. So those are the two surfaces I'm talking about, right? And there is no distance between them. Now, what we want to do is we want to have a coordinate system that is attached to the tip of the crack. I can put x and y directions conveniently. I certainly can, and I will. But instead of monitoring position in terms of x and y, what I will do is I will use a cylindrical coordinate system, and I will look at an arbitrary point, let's say located there, and that point will be indicated by a distance from the crack tip, which is r, and a orientation, which is indicated by an angle theta. And now at that point, I will look at an infinitesimal element. I will depict the stress geometrically, and I know that we have a sigma x, we have a sigma y, and ultimately a tau xy. Okay. Now we would like to calculate these values based on the loading of this plate, which is a far field loading through a stress S. Goes without saying, again, there is a stress distribution at the bottom portion. Right, and the way this is done is based on the assumption of linear elasticity, because that's what we are assuming is dominant presently. We're not looking at effects of braking or effects of plasticity. In fact, we are omitting plasticity altogether. We're assuming plasticity is not dominant, and we would like to calculate the stress field under the assumption of elasticity. That is why we call this topic linear elastic fracture mechanics, because we are basing our tools of fracture analysis ultimately on an analysis that is realized through the assumption of elasticity. Now, is that reasonable? It's not. To a large extent, actually, it's not, because we know that the stress field at the tip of the crack is so large in the y direction that no material can actually sustain it. But nevertheless, in some ideal world where failure does not happen through the ultimate strength of the material, and therefore those infinite stresses can be sustained, we are going to work with the tools of linear elasticity and we are going to calculate the stress components, right? Let me repeat that. In reality, okay, we are assuming a brittle material, so plasticity can be omitted, but brittle materials have an ultimate strength. We are thinking about an ideal world where the ultimate strength is infinite and therefore infinite elastic stresses can be sustained, and I'm trying to calculate the distribution of the stress in the vicinity of the crack tip at an arbitrary point away from the tip of the crack. Okay, and the tools with which this is done is coming from the tools of linear elasticity. We have a elective course, applications of solid mechanics, in which we consider and use and in detail such tools. And I'm just going to here write the final results. So the purpose of this course is not to derive the results for the stress fields, but actually just to make use of what appears in those stress fields. So I'm going to write the values for expressions for sigma x, for sigma y, and for tau xy. Now, it turns out that, first of all, the stress field will depend on r and it will depend on the angle. I know it depends on r because if I were moving along the x-axis, if I'm very close to r equals 0, the tip of the crack, sigma y will be infinite, but then it will rapidly decay. Okay? And I know sigma x also changes along that axis. Okay? And there is no reason not to think that it will also not depend on the orientation, because if I were moving instead of that direction, sigma y is here infinite, but if I move sufficiently far from the hole, I will hit that point where sigma y is s, which is a finite value. So both the distance and the orientation is going to influence the value of the stress components. So r and theta will appear, and the way they appear is as follows. There, it turns out, appears a factor, let me call it K1. This is an immensely important factor, a quantity that we're going to make use of, but presently let's just put it there without explanation. And then there is a scaling by square root 2 pi r, and this component, let me say, is the same for all the stress components. Okay? Well, does it make sense? To a certain extent. Let's say for sigma y it does certainly make sense. When r is equal to 0, I'm here and I know that sigma y needs to be infinite. Okay? We're just concentrating on sigma y at that point. Okay, so now the orientation will also make a difference, so there will be some dependence on theta as well, and that dependence comes as follows. For sigma x, there is a cosine theta over 2. Okay. In fact, for all of them, but then the rest is different for different stress components. Here we have cosine . Okay. I will explain what these dots mean. All right. Well, this is, it turns out, what the analysis reveals. Again, ultimately, what we are going to concentrate on is what K1 stands for and what eventually it physically means and how it will be useful for us. But presently, I'm writing these expressions so that we understand that these stresses, the stress field at the tip of the crack or near the tip of the crack is quite complicated. So for instance, for sigma y, okay, r goes to 0 and the stress goes to infinity, but also depending on the orientation, theta, the stress components will also change. Now, these terms are all terms which scale with terms that are of order 1 over square root r, such that when r goes to 0, the order sign here just indicates that because they are of order 1 over square root r, when r goes to 0, all of them blow up. Okay? Now, of course, whether they blow up or not depends on the value of theta as well. But presently, that's what we have written. Now, when r goes to infinity, therefore, it doesn't have to be infinite, but when it is sufficiently large, it seems that these terms are decaying to 0. But we know that sigma y cannot decay to 0. For instance, if I move sufficiently far from the hole, sigma y should not be 0. Actually, it should be equal to s. So there are actually here certain terms that are of order square root r, such that when r is very small, they become irrelevant because they go to 0. But when r is very large, this part becomes irrelevant and these terms take over. But these terms are finite terms, they are not very large stresses, whereas these terms have to do with values blowing up. So these are the terms that I'm interested in. These are the terms that dominate the stress field within the zone that is close to the tip of the crack. And these stress components are ultimately responsible for what we are going to call fracture. And within those components, there appears this factor Ki, okay, or K1. Now, what is that factor? Now, that factor is something that is known, and it is simply equal to S root pi A. S is the far field normal stress, and A is the half width of the crack, square root pi. Okay, now immediately embed this expression in your minds because it's something we have to know by heart. This quantity is called the stress, not concentration factor, but intensity factor. Okay, and it is the stress intensity factor for I, or 1, for mode 1. Okay. So, since I've called this mode 1, there is probably going to be other modes which I will briefly discuss in a second, and then we're going to work more on them in the future as well. So let's have a look at the units of K1 because it is strange. It has megapascals and square root dimension of meters, so it has units MPa square root M. Okay. Also keep that in mind, right? Now, what is special, first of all, about that factor? Well, that factor is a constant which involves only problem-specific parameters. Everything that is special to the problem setup, in this case, my problem is very simple. I have a plate, okay? It has a hole, it has a crack of width 2a, or half width a, and I apply a far field normal stress to it, which is S. So I'm not bending it, I am not, right, torquing it, I'm pulling on it. And that's the average stress, the far field stress is S. It appears in here. If I change the value of S, it will appear reflecting the value of K1. There is a crack half width A. If I change the value of the crack width, it will reflect in K1. Everything else that appears in sigma x apart from Ki, they've got nothing to do with the geometry of the problem. They're just geometrical parameters, r and theta, right? So everything that is special to the geometry of the problem is, or for that matter, to the loading, is embedded in Ki. So it involves all problem specific parameters. Okay, now this is our first exposure to this important parameter, which is called the stress intensity factor, in this case for mode 1. And in terms of that factor, the stress components have been defined. Now you might ask yourself, well, we've said that the stress field in the vicinity of the crack tip is a multi-axial stress state. It's not purely tensile along the y direction as the far field stress suggests, but it's complicated, and that complication comes in through the presence of the crack. So you might ask, well, what about the stresses that have to do with the z direction? So it turns out the stresses that have to do with the z direction, they are rather simple. So first of all, tau yz and tau zx are both equal to 0. And the value of sigma z depends on the type of problem that you have. If you have a plane stress problem, right, by definition it's plane stress, and therefore there is no stress in the z direction. But if it's a plane strain problem, remember we are assuming elasticity, and therefore directly from generalized Hooke's law, again we are assuming elasticity, and goes without saying, as I've expressed before in the rest of the course, we are using isotropy, and therefore directly from generalized Hooke's law we find that because if it is plane strain and not plane stress, that would be the value of sigma z. So sigma z is something we can post-process from the known stress field. All right, good. So we have our exposure to stress intensity factor mode 1, and we have stress fields that are described through that factor. We do not need to know these stress distributions. We don't need to understand where they come from. We just need to appreciate the fact that in the vicinity of the crack tip, despite the simple far field loading, the stress field is highly complicated. But that complication is mostly geometrical, right, through r and theta. All the problem-specific parameters are reflected in the simple parameter, the stress intensity factor, which we have to know by heart. So let's try to imagine what I'm trying to do here. What I'm trying to do here is I'm pulling on the plate, and when I pull on the plate, in that portion there is a hole, and that hole will try to open up because I am pulling on the plate. So that is why mode 1 is sometimes called the opening mode, right? It tries to open the crack opening mode. And one way to depict that in a slightly different scenario is the following. Suppose I had a specimen if you like, there can be a support at that point. I'm not going to depict it, but suppose now I embed a crack. I take a knife and just put a slit into this bar at this edge, okay, so that I create a crack surface, okay. And subsequently what I will do is I will try to open that crack by applying a load at the top and bottom portions. So as a result, what I will obtain is a picture that probably looks like this. Okay, so I am pulling, right? And because I pull, the crack surface, the surface of the crack will part from each other, and I open the crack. So this is mode 1. I try to open the crack. The geometry is not the same for the two problems, okay? So these fields are not directly applicable, but the idea is similar. It's a mode where I try to open the crack. So this is mode 1. okay? And you see that it has to do with some type of a tensile loading, okay? That's K1. So tension causes opening, right? And now we can think about what other things we could do with the same specimen. So I have a bar again, right? If you like, it is supported on this on the other surface, and I have actually, let's say, two such specimens. And in each case, I will take a knife and put a slit through the edge of the bar, and then I will try to load it in different ways. In this case, I pull on the surfaces and I try to open the surfaces of the crack, right? I try to open them. Now, let me ask you a question. What other types of loading can I apply to this surface, to this portion, let's say, of this bar where there is a crack, such that the crack surfaces do not open in a relative fashion, but they do something else, right? So, or you can think about the question in the following way. If I have two surfaces, I can open them. What else can I do to them? What other type of motion can I impose on the surfaces other than moving them apart from each other? So take a second to think about that by, if you like, pausing the video. Okay, but I'll go ahead and discuss the possible motions that we can impose. One thing we can do is, instead of opening these surfaces, I can try to move them with respect to one another. Okay, let's say in that direction. Okay, so in other words, instead of the upper surface moving up and the lower surface of this crack moving down, one of them can move in, one of them can move out. Okay, well, how can I impose such a motion? I can pull on the surface that lies above the crack, and I can push on the surface that lies below the crack. Okay, and as a result, I would probably obtain a deformation that looks like this. So this is where the crack was, right? And this is the lower surface of the crack, and I have pushed on the upper surface, on the surface that lies above the crack, and I have pulled on the surface that lies below the crack, right? So one part of the crack moves forward, the other one moves backwards, and this is what I obtain. The other thing I can do is I can try to move them relative to each other. Now, I can move them like this or like that. There isn't much of a difference. But I can therefore pull, or I can move them apart. I can move them in that or that direction. But what I can also do is, you can imagine, I can twist them like this, right? That's another type of motion I can try to impose. So I can do that in this case by pulling to the right on the surface that lies above the crack and pulling to the left on the surface that lies below the crack. And as a result, I will obtain a picture that probably looks like this. Now this one is a bit tricky to draw. here I can do a bit of an adjustment. Draw it like this. Well, I guess I haven't done a great job here, but still, you can imagine what I'm trying to do here is I am pulling to the right there, pulling to the left there, okay? And as a result, I am moving the surfaces, the upper and lower surfaces of the crack apart from each other in these two directions, but at the same time, they sort of rotate with respect to one another, okay? So now, therefore, we have three different types of motion. One, where the surfaces part from each other. Another one, where the surfaces slide with respect to one another. And one, where the surfaces twist with respect to one another. So this is an opening, this is sliding, and this is twisting. Okay? Now, this mode is called mode 2. And eventually, if we try to depict mathematically the stress field in the vicinity of the crack tip as a result of that motion, it turns out there are expressions which arise, well, not in this probably complicated geometrical scenario, but in a scenario that is comparable to that geometry, the stress field would be very similar to these, except that instead of Ki as a problem-specific parameter, there would appear a K2, and their definitions are very similar to the definitions of K1. We're going to see how they're defined eventually when the time comes. And in this case, this is called mode 3, and there would appear a parameter, problem-specific parameter that is called K3, the stress intensity factor for mode 3, stress intensity factor for mode 2, which governs the stress field. And eventually, we're going to make use of these stress intensity factors to analyze fractures in these different scenarios. Now, opening mode has to do with tension. Again, let me ask you a question, and you can take a minute to think about it. What kind of loading can I impose on a beam that is, again, if you like, it is supported on the other surface? What kind of a loading can I impose on this beam such that the surfaces undergo this motion? And in this case, what kind of a loading can I impose such that the surfaces can undergo that motion? Okay, now let me give you a hint. In reality, there would be a stress distribution here. So let's draw that with a different color, green. And I would generate that load through that stress concentration. And the statically equivalent representation of that distribution is a force in that direction and a force in that direction. Okay? So in this case, I would apply a distributed load at the top, distributed stress at the bottom, and I would push. Statically equivalent representation of that piecewise on the top and bottom surfaces, a force in that direction and a force in that direction. But ultimately, over the whole surface, what would be the statically equivalent representation of that stress distribution? Or for that matter, what would be the statically equivalent representation of this a set of two forces, or for this couple, to give you a hint? And similarly, in this case. Okay. Now, if you've taken a minute to think about it, you can see that you can statically equivalent representation of this distribution is a moment in this case. So it would be bending. And in this case, it would be torsion. Okay. So here I am trying to apply a bending moment in that direction. And here I am trying to torque the surface in that direction. Okay. Here bending is about the green axis. Here the torsion is along the axis of the beam. Okay. So whenever we have opening or tensile loading, we have mode 1. Whenever we have sliding surfaces in this fashion, that's typically induced by bending, we have mode 2 and an associated stress intensity factor K2, and so on for torsion. All right. Now, we are at this point, all we are trying to do is we're trying to motivate the presence of this new quantity and how it appears in, qualitatively how it appears in different loading regimes. In each case, what's special is that there is a crack, and that crack induces a complicated stress field with the special feature that at the tip of the crack, one or more components will blow up towards infinity. Okay. Now, but it seems that all of the discussion here, every expression that we have is highly mathematical. So the question we would like to ask now is, why are we talking about these expressions? Or let me simplify the question, why are these stress intensity factors important? Or let me simplify it further, are they physically relevant? Okay, and that's what we will try to answer next.